Good afternoon, everyone, and welcome to RTDology, Burns Engineering's online training series. I'm Jeff Wiggin, National Sales Manager at Burns, and presenting today will be Bill Bergquist, Senior Applications Engineer. Today's presentation, Temperature Measurement in Freezers, Autoclaves, and Air, is part of our continuing series of web-based training modules designed to help you better understand temperature measurement and achieve your measurement goals. If you've joined us for any of our previous sessions, we'd like to welcome you back. If this is your first time, welcome. And when you get a chance, do check out our previous presentations on our RTDology channel on YouTube. Before we get started, just a few housekeeping items. To respect everyone's time, we'll make every effort to limit the presentation and Q&A period to 1 hour. We do highly encourage questions, so please type them into the Q&A section or the chat box on your screen and send them to host and presenter. We'll attempt to answer as many as time allows. Today's session is being recorded, and we will post it on our YouTube channel, so don't worry if you miss something. Also, if we don't get to your question or you need some additional assistance, there will be contact information provided at the end of the presentation. And finally, our goal is to answer your temperature measurement questions and challenges. We've built our RTDology series around commonly asked questions and issues. However, if you have a topic you'd like to have considered, please do give us a call, and we'll see what we can put together for you. So that covers the housekeeping. So without further delay, here's Bill Bergquist to help guide the way in temperature measurement in freezers, autoclaves, and air.
Well, good afternoon, everybody. Today's webinar, we're going to talk about some of the challenges that are associated with measuring air temperature. And one of the biggest problems is that the heat transfer rate is a lot slower than in liquids. And then there's some things that we need to take into consideration to account for that. There's sometimes a lot of temperature gradients within environmental chambers, whether it's a freezer, incubator, even ductwork can present some significant challenges. This is a format we're going to follow. We're just going to go through how the probes need to be protected, where we place them in the process to get the best performance, talk a little bit about some calibration, interchangeability of the probe, some of the same things that we've done in other webinars when we talk about the performance of the probe. And then finally we'll finish up with the price and the service life for the probe. Autoclaves have a very unique environment for a temperature probe. They undergo a pressure change and there's steam involved, and they need to be sealed correctly through the wall of the autoclave so that the vacuum can be pulled. So the probe has to be designed to withstand those specific environments. Pressure change is the biggest problem with temperature probes. A probe that's not sealed up completely in a vacuum, the air will come out of the inside of the probe through the, like maybe it's an epoxy sealed cable that goes into the probe. It'll actually suck the air right out of the probe, and when they put steam back into the autoclave, that steam is going to go right inside the probe, and it's going to cause shunting in the sensing element coils, and you'll get too low of a indicated temperature reading. One of the best ways to help prevent this is to put this EPDM hose or some other hose material over the cable and have that run through the wall of the autoclave to the outside, and then seal it in through some sort of a fitting. This one has a little tri-clamp showed on it right here. Some of the other ways to handle this would be sealing up the sensor with some plastic injection molding or some sort of molding system where the sensing element is completely encased and then molded right to the cable jacket. So that creates a continuous waterproof seal for that temperature sensor. Then that cable has to be run out through the wall of the autoclave. And that results in some other issues. As you can see in this example here, the lead wires were run through what looks like it's a tri-clamp fitting, and they had some kind of a cord grip installed into it, and then they covered it with silicone rubber because apparently that didn't quite seal it in real sufficiently. So building that hygienic ferrule or tri-clamp fitting into the probe itself is one way to improve that connection. This example has a the tri-clamp fitting connected to this hose. This particular hose is one that has a Teflon liner in it, and then there's a stainless overbraid over that, and then there's a silicone rubber jacket over the top of that. So it's very watertight, very durable. This one also features a replaceable probe with this little compression fitting here that can just be undone, and the probe would pull out of the sleeve. So that's a couple of good features to look for in an extreme duty temperature probe for an autoclave. In some instances, we have cases where you need to run multiple sensors into an autoclave. You might have a couple on some items that are inside and maybe have another one just hanging down in the middle of the autoclave to monitor the temperature. So you need to run multiple probes through the same fitting in the autoclave wall. And this fitting allows you to do that, 2 or more. Depending on the size of the tri-clamp, you could get several feed-throughs. And that hose covering on the probe just attaches to the little hose barb fittings here. Durability is also a huge issue. A lot of the probes used in smaller autoclaves just will have a silicone rubber insulated cable. And that cable tends to snag on things, and it's not real durable. It tears fairly easily. One of the things that does help is to get silicone rubber cable that has a special coating on it that makes it less susceptible to snagging on things. If durability is an issue, the next step up from this style probe would be to go to a cable that has the hose covering over it. And then looking at this one again, this is designed for the big walk-in style autoclaves where somebody may hook this onto a hospital bed, for example. And what I had heard from several customers is that when people are removing the equipment from the autoclave, they'll forget to detach the probe from the bed, and they're rolling it out, and you get to the end of that cable and something's going to break, and it was usually the probe is just going to fall apart. This one should be durable enough to actually stop the hospital bed when they hit the end of that cable. One other thing to look for is on the sensing element themselves is you want, besides the hose and the setup through the autoclave wall, got to pick a really heavy duty temperature probe. And one of the best ways to do that is with a thin film sensing element. And this is an enlarged view of a thin film platinum resistance sensor. You can see the little platinum traces right here. When these are packaged correctly, and I have to stress correctly, they can be extremely durable. So a sensing element like this in an autoclave probe, you can drop this on the floor, you can bang it around, and it's not going to hurt it any. Wire wound sensors, on the other hand, can be damaged quite easily by like dropping them off of a hospital bed onto the stainless steel floor in an autoclave. The one thing that you do give up a little bit with the thin film versus the wire wound would be some long-term drift. The thin film tends to drift a little bit more. It's more difficult to get a tighter interchangeability tolerance with them. So a little bit of a trade-off, but usually the durability is a much more beneficial feature than having like a wire wound sensor that can have a tighter initial tolerance. That initial benefit you get with a tighter interchangeability tolerance can go away quite quickly if it's dropped a couple times, and that the platinum wires tend to work harden, and then the resistance will change, and then your initial accuracy benefit has gone away. So with that, I don't know, Jeff, you can kind of keep us posted if there's any questions popping up.
Yeah, so just want to remind everyone that if you do have a question, feel free to ask it, or if you need any clarification, go ahead and type something into the Q&A section or the chat box, and we'll go ahead and address it kind of as we go. If you've got a more in-depth question, you want to wait till the end, that's fine as well, but feel free to type them in as we go, and we'll try to get answers to your questions.
Yeah, so we move on to freezers, and these have some other issues. First, the biggest one is water. Anytime that the temperature probe is taken out of a freezer, frost is going to accumulate on it, and it's going to melt, and then thing's going to be sitting there in a pool of water. A typical RTD probe, if it's just like an industrial grade, whatever, got some cable coming out of it and it's potted with epoxy, water's going to leak inside of that, cause that low temperature reading. And placement within a freezer can be an issue also. So we've got temperature gradients that are typically in a freezer. It's going to be coldest at the very bottom, warmest at the top, depending on how the freezing coils are set up and things. So we have to look at where those warmest and coldest parts of the chamber are and set the probe in, typically in one of the warmer areas, so that you'd want to make sure that whatever you're trying to freeze gets down to at least your minimum coldest temperature. And then you want to make sure that frost doesn't build up around it, because that's going to slow down the time response, and your freezer could shut down and the probe would still be saying it's the right temperature 2 hours later because it's buried in frost. So those are just a couple of the real important features to look for in a temperature probe. Some of the waterproof designs, they'll look pretty much just like any old RTD probe. These examples here are ones that are actually molded in, I think it's FEP or Teflon. And then they also have an epoxy seal in the back end just to keep liquid water from, filling up the probe. And you really can't tell by looking at the probes if it's a waterproof one or if it's just a regular one. You just have to make sure that thing was built with the usage in mind. One of the other features to look for in freezer temperature probes is the time response. Probes that respond too quickly can actually set off unnecessary alarms. Someone comes in to load the freezer, pull things out of it, and the door is going to be open for 2, 3, 4, maybe 5 minutes. You don't want the temperature probe sensing that initial blast of warm air that comes in. a couple ways to slow down the response time of the probe. If you have a transmitter in the measurement circuit, a lot of them will have a response time setting. This one, I think, had like 1 to 40 or 1 to 60 second delay time. Another good way to do it is just to add a Teflon sleeve over the sensor. It slows down the response time quite a bit, and you can add, even if it's just maybe shrink tube or even a thicker Teflon block over the sensor. And then one of the other common methods is to put the sensor inside of a bottle filled with glycol. And that one will get you about maybe 10-15 minutes of delay time before that fluid temperature will change enough to register a change in temperature in the freezer. And then ambient air temperature. Now, again, we have the really slow response time issue with this. We also need to look at radiation sources, whether it might be from sunlight or if you've got a heater inside a building or a pipe that's got a hot fluid in it or a cold fluid. Those things can affect a temperature probe. We had one situation where temperature probe was installed in a factory, and initially it worked just fine, and then after production got going, it wasn't reading correctly, and that was tracked down to a fan that had gotten turned on, and it was just causing the air to move around this sensor and giving a lower than actual reading because it was blowing air from some other location into this other area. So those are some things you have to watch out for. Simple little radiation shield. The probe is outside. This one, white PVC. Anything white material usually works pretty good. Plastics, since it has such a low conductivity, are a good choice for that. Some examples of air temperature sensors. A couple of wall mount styles. This one, either of these will mount into just a standard junction box. This one over here is a heavy-duty version. Might be used in a warehouse. Also in a completely explosion-proof. So if there's some hazardous gases or dusts around, that would be a good choice to look for. Got a guard tube over it, so it makes it a little bit forklift and careless, whatever, proof. And if we're measuring temperature inside of ductwork, there's a couple of rules of thumb that you may have seen out there. Like 10 times the thermal wall diameter, insert at least 2/3 of the duct size. And I guess what I have found that neither one of those really work very well. There's a lot of ifs and buts that go into this, and you really need to look at each application specifically and what the flow rate is, whether it's an insulated or uninsulated ductwork, and what if it's round or square, that can actually make a little bit of a difference. Because there's going to be a little bit of a boundary layer associated with ductwork, and you need to take that into consideration. Room air temperature. Typically, they'll put these on a wall that's the furthest from the heat source. And one thing that gets overlooked frequently is when you mount these sensors into a junction box, into a wall. So the sensor will be on the surface of the wall, but you really need to insulate that junction box so that whatever's going on behind the wall covering isn't going to affect the temperature sensor. Because you want to isolate this little sensing element. The sensor in this one is just located right behind this little grill work here. You want to isolate that from whatever's going on inside the wall that it's mounted to. And another application here where a customer had installed some 1/4-inch diameter sensors in a ceiling, and they extended down about 3.5 inches into the room. The connection head was above the ceiling in quite a warm space, much warmer than what the room was, and they were seeing a pretty significant temperature error. And what was happening there is that they were getting a stem conduction between the connection head where it was 90 to 100 degrees and where the temperature sensing element was located, which just about 3.5 inches below the ceiling where they're trying to control to 70. And what happens is that heat from here will conduct down the probe sheath and the lead wires and the insulation and whatever else is in there, and it will have an effect on the sensing element. So you're going to be reading partially this warmer air above the ceiling. Turned out to be a fairly simple solution. They didn't want to go any lower than 3.5 inches, so we put a 90-degree bend in the probe and had it just extending out horizontally at the ceiling height, and that completely fixed the problem. We just needed about 12 inches of probe length in the conditioned space to get a good accurate measurement. Now, situations where you want to do more than just a single point measurement, there are averaging sensors. And what these are is just, if you can imagine, a little coil of platinum wire just stretched out over the full length of this coil. I think this one happens to be about, I don't know, probably looks like about 50 or 60 feet long. So that sensing element is just stretched out over that full length so that you get an average temperature over that length. These are typically bendable so that if you're in a ductwork, for example, you can do some S-bends or zigzags, or you can leave it in a coil and just stretch the coil across the ductwork. And that'll give you a good average temperature of what's going on inside that duct. And when installing these, and even a single point sensor inside of ductwork, you need to take into consideration the boundary layer. If you have a real low velocity, you're going to have a thicker boundary layer than if you have a higher velocity. If the ductwork is insulated, that tends to minimize that boundary layer. But you want to get the sensor past that stagnant air boundary so that you get into the good, clean flow that's representative of what the temperature is inside the ductwork. One thing I didn't mention here was that a lot of averaging probes like this will have you specify a non-sensitive length. And that is just to get that sensitive portion of the averaging sensor through that boundary layer and into the clean flow. This one looks like it has about a 4-inch little dead space there. So, and then that kind of covers how we protect the probe on the inside of the process. We have to make sure in some cases where it's waterproof, time response is appropriate for the application. We also need to protect the probe on the outside of the process, and this is done primarily with the connection head. A lot of different styles around explosion-proof, waterproof, stainless steel, plastics, hazardous atmospheres. There's FM, CSA, ATEX, and on down the list, methods of installing into hazardous locations. So, and with that, Jeff, I don't know if we got any questions. Feel free.
Yeah, there's a before you head on. There was a question. It was back when you were talking about autoclave sensors, and the question is, do you use the same methodology for HAST or HAST chambers, which are highly accelerated stress tests? So that would it would be similar, except that there's some special considerations. On the autoclave side, you have a vacuum that's being pulled, but typically there's pressure applied with the stress test chambers. So that would kind of change the design of the sensor potentially, because you need to make sure that you're able to account for that additional pressure depending upon what that pressure is. So they're for people who aren't familiar, they're typically high humidity, pressurized test chambers that are trying to accelerate the findings. So it would be similar, but there's some special considerations that would need to be taken into account based upon the specifics of the application.
All right. Well, that sounds pretty good. So I wanted to move on to performance here, and looking at the things that come into play with the error budget. We have the sensor accuracy, which is usually a pretty small number. Some of the bigger numbers are actually have to do with the way the sensor is installed into the process. And both of these together kind of make up your sensor accuracy. And we need to look at all of those. Two of the biggest ones are, of course, time response, and then stem conduction can also be a fairly significant number. First off, interchangeability. When manufacturers make an RTD probe, they adjust the resistance of the temperature sensor, the little sensing element, to 100 ohms at 0 degrees C. And then there's a tolerance associated with that, because, of course, we can't always hit it exactly at 100 ohms. A couple of standards define those tolerance grades. So there's the ASTM spec and then an international standard. And so at any temperature you may be interested in, you can calculate what that interchangeability number is. At 0 degrees C, this factor drops off, so we're just left with 0.13 degrees C for the grade A or 0.25 for the grade B. And then the IEC standard has a little wider tolerances. So they go up from 0.1 up to this 0.6, this is a new class that they're adding. I think it may actually have already been added in there. There's also a graph, and we have the tightest tolerance rate here at 0 degrees C, and you can see here as we go away from 0, the tolerances get bigger, and that's exactly what the equations will help you define. Again, here's the IEC standard and the ASTM. Just a little bit of difference in the tolerances between the two. Now, when we're looking at choosing a probe for a particular measurement point, it really pays to look at a high quality, accurate, repeatable, stable sensor that's installed correctly, because it's going to pay for itself over time quite quickly. We have all these factors that come into play when we're looking at the total cost of that measurement point. Usually the initial cost is one of the lowest pieces of any of this stuff. If you have a cheap probe that breaks all the time, you're going to need to keep more in inventory. You got somebody going out there to change it. You might be using more or less energy than what you need. If it's less energy, your product might not quite come out like you want it. So there's potentially some scrap. So really high quality, installed correctly, it'll pay for itself over a very short period of time. The other thing I wanted to talk about is just some other types of air temperature measurements. One that I was involved in years ago was total temperature, and these are typically used on aircraft for setting engine power settings and calculating airspeed. They take lots of different shapes. They have to be able to withstand bird strikes, hail strikes, all sorts of abuse. Some of them have de-icing heaters in them so that if you're flying through some precip at altitude, the water will start to freeze on the thing, and you need to be able to melt that off and not affect the measured temperature. They also have a feature where any particles that are in the air will pass through the sensor without actually going past the sensing element, because the particles could actually start eroding that sensing element and cause a short lifetime. So they have some different airflow features that allow that. This one here was for the V22 Osprey, just an outside air temperature sensor. This type would be typically installed in the inlet of a turbine engine. A lot of military applications for that style of probe. The Harrier, the vertical takeoff jet, uses this style. It's a little bit taller. And then this probe here is one that is used on a test boom that would go on a experimental aircraft, and so they'll have a boom sticking way out in front of the nose of the aircraft, and it would be in the very clean airflow, and it has an exposed platinum wire doing the temperature measuring. So it's very fragile. They typically get about, lifetime's usually measured in hours, but they need the quick response of that type of a sensor in those situations. 747, there's a couple of these sensors. There's two of them mounted right up by the windshield, and they use those for airspeed calculations. An example of one hanging in the engine inlet. This happens to be on an Airbus A320. And you can see the close proximity to the turbine blades here. Strength, durability is hugely important, as is de-icing. So you don't want a big glob of ice forming on this and then breaking off and going through that turbine. That's just asking for a disaster. On some of the smaller biz jets, the total temp sensor is located down about the 4 o'clock position on the fuselage. You also see it down here on several of the Boeing jets, some of the smaller ones. And with that, I guess I'm all wrapped up here. Just kind of wanted to repeat again, especially autoclaves, durability, and sealing for pressure changes is hugely important. Freezers, pay attention to the liquid water. Make sure the temperature probe is completely waterproof, that your cable and the probe are suitable for the cold temperatures. And with room air temperature, having sufficient immersion length to take stem conduction into account, and then look at the temperature gradients within that chamber, and place the probe where typically in a freezer you want to put it in the warmest place. If it's an oven, you might want to put it in one of the cooler places. If neither one of those locations are good, then an averaging style probe may be suitable for what you're trying to accomplish. So with that, I think I'll turn it back to Jeff here, and we'll see if there's any other questions.
Thank you, Bill. Appreciate that. Yeah, we do have, first a reminder, I just want to let you know that the session is being recorded, and we will post it to the RTDology channel on YouTube. So you can go there to see the whole thing if you've missed anything, or if you want to send it along to somebody else, feel free to go ahead and do that. If you do have any questions, go ahead and type them into the Q&A or the chat section, and we'll get them answered. We do have a couple minutes here. There is a question here about using glycol, so I'm assuming this is in a freezer application. Yeah, it is. If the freezer sensor is in glycol, is it recommended to use glycol bottle for the standard sensors while conducting annual temperature mapping?
I would say no, because the glycol bottles that I've tested tend to have a very, very slow response time. And if you're doing temperature mapping, you're typically not going to be opening up the freezer door, I wouldn't think, and you're going to want to know if you have an area within the within the freezer where the temperature is changing quickly for some reason. It might be a fan that's blowing, and just the way the air is circulating, that there might be a dead spot somewhere where it's not getting mixed up correctly. And you'd want to know that pretty quickly, and using anything to slow down the response time probably is not a good idea.
Okay, thanks, Bill. Appreciate that. If you do have any questions, go ahead and type them in, and we'll get to them here today. If you don't have any questions, you think of something a little bit later, feel free to go ahead and contact us at the contact information. Was that the previous slide, Bill, or?
Yep, no, this is it.
Here it is. Okay. You can go ahead and contact us, and we're more than happy to help you out with your application. Try to get your questions answered. So doesn't look like we got any other questions. So Bill, any final statements?
No, I guess if you want to get a hold of us too, you can do it through the YouTube channel also. There's a place there for comments. And we always appreciate any kind of feedback on the webinars here, anything that you'd like to see us add, new topics, just let us know.
Okay, and as a reminder, our next RTDology session is coming up in February. Be RTD or thermocouple, what's the right choice? For those who have been wondering what's the difference and which one should I use, this would be the perfect opportunity to find that out. So with that, it doesn't look like we have any other questions. So wishing everybody happy holidays, and enjoy yourself. Don't eat too much, and we'll see you in February.